Why don't we go ahead and get started? So hello and welcome to this AIAA AviationX webinar presentation. I'm Jim Sherman. I'm the Senior Director of Aeronautics here at AIAA. Today, we are pleased to share with you a presentation that was originally scheduled as part of the 2025 Aviation Forum 360 program, NASA Aeronautics Vision and Outlook. The timing for this presentation is fitting as the Aviation Forum 2026 call for content is now open. So if you are doing amazing things in aviation, we invite you to submit a technical paper abstract or session proposal to the website listed on the chart. The portal window will be open until November 13th, and we look forward to receiving your inputs and seeing you in San Diego. So let's get to the webinar. Let me introduce today's moderator, Dr. Richard Walls, Sustainable Flight National Partnership Mission Integration Manager at NASA. Dr. Walls, all over to you.
Thank you, Jim. We really appreciate AIAA hosting this webinar and really look forward to it. We've had a long relationship with AIAA, and since 2013, when the forum started, NASA Aeronautics has really hosted a Forum 360 where annually we'd give a kind of a state of NASA Aeronautics and then have a themed panel session. And this past summer was the first summer that we weren't able to do that, but we really wanted to get the word out, and I know Bob loves answering questions, so we're not going to have a panel session today, but Bob will give the overview. So to introduce Bob. He's been with NASA for just about 35 years, maybe a little over 35 years. In the last 15 years, he's been kind of in the front office of NASA Aeronautics. And since 2019 is the Associate Administrator for Aeronautics. He had a stint in the middle there where he was a Deputy Director for Next Gen Air Transportation with the JPDO. So he's got a lot of coverage across all of aeronautics, all in aviation. He did receive his bachelor's in 1983 from Syracuse, go Orange, and a master's at MIT in science, technology, and policy. And I know on the side he enjoys watching a good soccer match. So with that, I'll turn it over to Bob, and we'll look forward to your questions.
Thank you, Rich. And just thank Rich for all his service over the years to NASA and AIAA as well. Let me add my thanks to AIAA for hosting this. Sorry I wasn't able to be with everyone at the Aviation Forum this summer, but certainly great to be with you now. Provide you a bit of a look at where we go from here. So we can go ahead and flip to the chart. There you go. Thank you. So I thought I'd just start with a perspective on our vision going forward. And for many of you, hopefully, this will look somewhat familiar. We've had for many years now a quad chart that kind of reflects our vision for transformation across aviation, and this is updated, and it has a couple of reasons behind the update. One is certainly opportunity. We've learned a lot over the last decade, and it gives us an opportunity to think about how we would reflect on what the big challenges are and the transformations we are looking at going forward. But also, the reality is that the aeronautics budget going forward is now, the president's budget request is $588 million, which is about a 40% reduction from the budget in FY25. And so we're looking at how do we continue to deliver value like we always do, but what are those transformations? What are areas where we believe we can add significant value perhaps with focusing a bit more on our internal workforce and the partnerships that we can create between our internal workforce and the partner community, the customer community out in the industry, and certainly with universities and so forth. So we'll reflect a little bit on that. But just to talk a little bit about this chart, then you can see in the upper left-hand corner, we've had an ultra efficient aviation transformation, and this continues to reflect that ultra efficient aviation transformation, but with a little bit of change. You can see in the upper left part of the upper left-hand part box, the transonic truss brace wing, which we was part of an overall portfolio of technologies that we were preparing for maturation with industry cost share partnerships for next generation transport class aircraft, and we continue to work on many of those. We did have to terminate the electrified powertrain flight demonstration, but we have sustained our effort in the transonic truss brace wing or the subsonic flight demonstrator project. I'll talk a little bit more about that. And of course, our high rate composite aircraft manufacturing, which is looking at how do we increase the rate at which composite aircraft can be built, so that single aisle aircraft that are produced at higher rates would be compatible with the fully composite both fuselage and wing section aircraft, and then advanced turbine engines with our high tech investment, our hybrid thermally efficient core project. So we continue those three. Again, we did have to terminate EPFD, but at the same time, in the lower right, we're starting to look at, okay, what's next? As we complete those large projects, what's next in ultra efficiency? And I'll talk a little bit more about that. But the image there, which is a image from the University of Illinois that they're working through one of our University Leadership Initiative awards. You can kind of see that if nothing else, you see that the unique fuselage shape, but also the multiple turbine engines or multiple propulsion units there. So a really interesting propulsion airframe integration problem. And of course, with this, it's focused on cryogenic hydrogen as the energy source. And so there's, I think, a lot of opportunities for the future to think about how do we continue to drive efficiency, greater and greater levels of efficiency into the aviation system, which has been, that's been the history of aviation is through technology, increasing efficiency, and through efficiency, reducing cost and driving up the ability for people to fly and to do business globally, to vacation globally, and to connect with family and friends and so forth. So we continue to do that. In the upper right hand corner, high speed flight. So I'll talk again more about that. But the X-59 in the foreground there, which is very close. We're just a couple of weeks away from first flight of the X-59 and the start of our Quest mission to demonstrate a reduced sonic boom signature, a sonic thump, that hopefully when we do the community over flights, we find to be acceptable to communities and therefore a basis for supersonic noise rules going forward. But then you see in the background there, right, a hypersonic concept and so forth. And so we now wanted to put that deliberately on the image to indicate that we continue to make progress in our hypersonics portfolio, and it's an area where we see the potential for greater focus in the future. Certainly consistent with our partnership with DoD, and DoD's significant investment in hypersonics gives us the opportunity to not only support DoD, but also then to use that as a platform, that partnership and the technology we're doing as a platform for looking at civil and commercial uses of hypersonic flight. In the lower right hand corner, of course, the great work we do in airspace and safety working with the FAA and with the airlines and the entire community, including, UAS, eVTOLs, high altitude long endurance, UAS, and eventually supersonic and so forth, to really bring all of it together. And of course, with the FAA working towards their brand new ATC system, it gives us an opportunity to support them in the near term while we continue to drive towards the longer term needs of the system. Again, in full partnership with the FAA and the industry. We had in the past a breakout for advanced air mobility. Again, this is an opportunity in this case to really reflect on the fact that there's a tremendous opportunity to think about the future airspace system as a whole, and that advanced air mobility is an element of that overall airspace transformation. So bringing those things together, driving those things together. The other piece is to really emphasize that airspace and safety need to be worked together towards a single perspective of how the system is going to operate and how we're going to maintain safety. And so we'll talk more about that. And then finally, in the lower left-hand corner is a new area. In some ways, it's maybe the most traditional area of focus for NASA Aeronautics, but one that we're bringing to the foreground to emphasize the ability to do more in this space as we see advancements in high-end computing, in machine learning and AI and so forth, the ability to really think about how we research and develop our engineering methods like computational fluid dynamics, which is what you see there. And I think having an eVTOL there is apt for a few reasons. One, it indicates the complexity of the kind of flow fields that are created with that kind of a configuration. And so one of the unique things I think NASA can do is develop those canonical experimental databases that allow us to drive higher and higher fidelity into our CFD codes and so forth. It also recognizes that over the last few years, as we work with the eVTOL industry, and really recognizing that our tools, the NASA developed tools, have been the basis for their ability to analyze their designs, do acoustic modeling of their designs and so forth, and that further advancement is required to continue to get higher and higher fidelity and be able to really make sure that these designs are optimized. And of course, everybody's, we're in the middle of lots of companies out there designing and building. This will be a Gen 1, and there's lots of gens to come as eVTOLs become a part of the system. And so we need to continue to drive forward on that. But more broadly, these physics-based methods and the ability to drive those forward in all domains of aviation and aerospace, which is why we say aerospace. I mean, we do this with launch vehicles and so forth. This is a real opportunity for us, not only to continue to emphasize an area where we've had decades and decades of leadership in the past, but also to help recognize that the work we do here can support NASA's exploration efforts as well. So I'll talk a little bit more about that. So taken together, I think this represents an opportunity to reflect on the changes we've seen over time and what we can do to emphasize value with our in-house workforce, but to continue to work with the overall aerospace industry and partnership community, because that's ultimately where value is derived when we're working together, when our methods, where our technologies and our learnings are transferred and utilized by the industry to produce systems that drive aerospace forward, drive aviation forward. So really, so there's a start, and we'll continue to think about this vision going forward and how well we can implement that, and certainly looking forward to the feedback of the community. I would just mention that in the revolutionize engineering methods, we've got a lot of discussion going on right now on that topic, and I'll talk more about that. So next chart. So just wanted to, there's a little bit inside baseball for those of you who are very familiar with NASA Aeronautics. This will I think you'll recognize this. This is how we're organized to implement that vision, to achieve that vision. And I just wanted to put it up here because with the more constrained budget and the need to become more efficient in how we do our business, we have consolidated some of our projects in order to drive that efficiency in how we do business, to make sure that we're putting as much funds into the research itself and the technology development itself and the testing itself as possible. So this reflects that. So I won't go through all of this, but just maybe a couple of highlights for those of you that are familiar. That under advanced air vehicles, that subsonic vehicle technologies and tools project is now composed of what had been the AATT, the Advanced Air Vehicle Tools and Technologies project, but it's also has RVLT in there, Revolutionary Vertical Lift Technology and High Tech that I mentioned. So that provides greater trade space as we look to the future, and again, with reduced resources, gets a project of sufficient size and so forth that we can manage efficiently. You'll also see that high speed where we put the commercial supersonic technology and hypersonics together into a high speed trade space as we look to the future. In airspace operations and safety, we had a separate airspace and safety projects, and we've put those together. Some of that is around efficiency, but some of it's around the fact that I do think as we look to the future, it's become more and more clear that as we look at system-wide safety and as we think about operations of the airspace, those two things really need to be worked in tandem to make sure that they are synergistic and are coupled as we look to the future. So putting those in a single project will help drive towards that kind of collaborative and synergistic thinking towards common views of the architectures that we're going to go towards for the future, the concept of operations for the future, and so forth. And below it, advanced air mobility Pathfinders project, that has been what we've been doing at AAM. We've also consolidated our CERO, our wildfire project, in there. Again, reflecting the fact that there's synergy between the work we were doing on the wildfire side, which pulled out on many of those advanced air mobility technologies, with our primary advanced air mobility project. Integrated aviation systems, to the right of that, you can see that the electrified powertrain flight demonstration project is no longer there, reflecting its termination, but the other projects continuing. And transformative aeronautics concepts, we terminated the Convergent Aero Solutions project, which was personally quite painful. That was I think a really significant project for both the development of the aeronautics workforce at NASA, but also the pushing towards a new culture for research, where we're really driving towards transdisciplinary thinking and multidisciplinary projects, so that we think differently about what those challenges are, think differently about how we formulate solutions, and then run fast at those with a light management, a light touch approach, and so forth. So while we have terminated that project, we are trying to keep, in fact, we are keeping the kind of the spirit of CAS, that CAS way front and center in all of our other projects, so that we are continue to do CAS-like projects within the aeronautics portfolio, because I think that's really important as we look to the future. Aeroscience evaluation and test, that's our large wind tunnels, and I'll talk more about some of the changes that we're making there. Next chart. I'll just really briefly, this is our budget request for 26. This is what was in the congressional justification report and was briefed to Congress and so forth. It is a $588 million budget through the out years, down from, again, $935 million in 25. Maybe the most important thing, and there's a lot of words on this chart, I apologize for that, but maybe the most significant thing here is just that Obviously we don't have yet a FY26 appropriation, so we don't actually know what level will be appropriated at. But we will, obviously as that gets sorted out, and we get to a continuing resolution and then an appropriation, we'll certainly implement at the levels that are appropriated for us. But nevertheless, we will continue to move forward in terms of the planning we've been doing in this that I just mentioned relative to our vision and so forth. So it doesn't change that they're leaning forward, that we are, we're not looking to go back, but we're looking to go forward. So at whatever budget level we're at, we'll do just that. Next chart. So let me just talk a little bit about some of the details here again on ultra efficiency. Next chart. So I won't go through again all the projects that we've had for the next generation. Other than EPFD, those projects continue. I did want to mention here on the transonic truss brace wing, the subsonic flight demonstrator, we are working with Boeing on looking at how we revise our approach there, but still a focus on maturing thin wing technology as extremely promising technology for the next generation, and we will continue to evaluate the transonic truss brace wing, and we'll see what makes sense relative to whether we want to actually fly an X-plane there, or if we will just focus on ground-based research. But nevertheless, again, we're going to focus on that the thin wing first, and then truss brace as a specific instance of thin wing technology, which again you can see at the bottom can yield significant reductions in energy use in aviation, which again translates to benefits to the airlines, benefits to the traveling public. Next chart. And at the same time, as I mentioned, while we continue those cost share partnerships, drive towards getting that technology matured by in the that 2030, prior to 2030 timeframe, we are, as we need to do, start looking at what's next, because it takes a lot of time and work to sort through all of the potential technologies, configurations, integrations that can occur for beyond next generation systems. And I think as we look to the future, as always, propulsion is just an absolute key to achieving greater levels of efficiency. And I think there's an opportunity as we look at that to look at multiple energy sources that could drive new approaches to achieving ultra efficiency, to driving fuel burn down. So we could start looking at, again, new energy sources. We can look at dual fuel. We can look at all those things. On the left-hand side, we, as many of you know, we awarded some ACES study contracts. You can see the awardees there. They are busily working those conceptual studies that will then be delivered to NASA so that we can take a look at all of that and start to look at what those big ideas are, and then start to think about what those big technical challenges are that would be required to achieve those big ideas. And on the right-hand side there, again, we've had ongoing work in things like hydrogen and electrification and so forth. But there's a lot of things that we can be looking at, taking electrification to another level, right? Thinking about when we think about cryogenics and superconducting, you can think about different, again, back to different fuels, different ways to actually utilize those fuels. Like in hydrogen, are you going to burn it? You can use a fuel cell, and potentially, methane, other things like that. So there's a huge trade space, and I think that's a place where, again, NASA can do a lot to help sort through that enormous trade space. Really look at what's promising, look at what the technical challenges are, and what it would take to overcome those technical challenges, the timeframes it might take, and so forth. And and that really helps the overall community move forward towards these really big new ideas. So I think this is, we're starting now, but if you look at our history, right, it can take 10 years to really work through that kind of complexity, so we can really narrow it down to a handful of things, just like we did with transonic thrust brace wing and high rate composite, so forth, just like we did there. What are those next things that will then, over time, we'll focus in on and try to put those things over the goal line with technology maturation projects. So that's a long-term process that we're just getting on the path to. All right, next chart. High speed. Next chart. So really exciting. We have been working towards the Quest mission, towards the opportunity to get the data, the community response data to a sonic thump, and deliver that to ICAO to get a community noise standard, get to a standard that industry could work to for commercial overland supersonic flight. We are, like I said, we're very close. We just completed the planned taxi tests of the X-59, and now we are moving into kind of the final preparations for first flight. So a lot of hard work going on right now. Huge shout out to the team that's working this. They're working tirelessly to try to get everything buttoned up and get the airplane off the ground. But once we get off the ground, of course, it's a whole process to clear the envelope for safety. And so, there's months of flight tests to make that happen, to clear the envelope. And then once we clear the envelope, we'll move on to acoustic validation. So we know, is the airplane delivering the noise signature that we designed to? And overall, let's characterize the noise, and that way we'll be able to do the planned overflights. We'll be able to be predictive in the noise that we will deliver during phase 3 in the community response test. And of course, all the attention tends to get put on the aircraft, but there's just so much other work going on. The development of microphone arrays that can be put throughout the communities that we overfly, so we know exactly the noise that's being delivered to the community. The fast time models of day of flight operations, so we know the exact flight conditions to deliver the noise signatures. Different models for geography, for building types, and so forth, that allow us to be very accurate in our predictions and so forth. So just so much work going on in addition to the vehicle. That's all going to come together when we get to that community response test. So we're really looking forward to that. But first step is getting the airplane wheels up, and we will do that in the coming weeks. Next chart. Let me talk a little bit about airspace and safety. Next chart. I think this is a little bit of a busy chart. Apologize for that. But the future, and with FAA focused on the brand new ATC system, there's a real opportunity, because what that will do, in my mind, I'm certainly not speaking for the FAA, but in my mind, you get to a recapitalized system, right? One where we have modern technology throughout the system that allows you to better accommodate advanced automation and so forth, and then the implementation of some type of a common automation platform, which is, to me, it's a baseline upon which you can then really start to think about and to grow towards all the functionality you would need to support an airspace system that not only will reflect the growing needs of airlines, but also the needs of eVTOL operators, advanced air mobility operators, UAS operators, high altitude, long endurance, and so forth. So lots of things. But this chart, again, busy, but it kind of speaks to some of the core elements of it. So in the middle there, that use of digital services, right? So once you've got this really a fully digital system, right? So the infrastructure is fully digital. you can then start in an architecture that reflects that. You can start to think about how you deliver digital services. So that's a key element of the NASA program. To the left of that, then, what can you do? That's actually an image of a tool that has been operating in Dallas-Fort Worth, the pre-departure planning tool, that uses that kind of thinking. So this is a tool that American and Southwest and others have used to look at their departure trajectories in the presence of weather in real time, determining if there are more efficient ways to get through the terminal airspace in a conflict-free way from other traffic, and then getting those asks digitally to the FAA for a quick release and departure, so that there's money is being saved. Well, that's the notion of third-party services and a federated architecture that's driven on a digital services backbone. So you really start to see, this a start of what that future could look like. And then on the right-hand side, again, on top of that, as we get to that view of what those future operations look like, that gives us also the platform for how we think about system-wide safety assurance, right? So if we are going to be safer going forward, we don't want to wait for incidents and accidents. We want to be discovering the risks and hazards, and then mitigating those before they materialize in the system. So by having that close partnership, that close synergy between how that operation is going to evolve in the future, and then how we assess that, I think is going to be really critical. And already we are delivering things to the FAA to enable MLAI-based data mining and analysis of the ASIA system and so forth. So there's lots of things in the near term, but transformation for the long term to make sure that the system stays as safe as possible. And then on the next chart, if we go to the next chart, yeah. At the same time, go back. At the same time, then we are, as we're looking at that core system, we are doing, the work, and we just finished up our partnership with the FAA and industry at FAA's key site in Dallas-Fort Worth to support them in the beyond visual line of sight rulemaking. That's now out for the notice of proposal rulemaking is now out. We played a key role there in terms of how that test was performed and data analysis and so forth. On the right, we continue to drive towards, that middle box is all around UTM and taking the next steps on UTM. On the right, it's about how do we develop provider services for UAM and federate that airspace. And then on the left, let's also bring this to emergency response use. So that's an image of a portable airspace management system for wildland firefighting. V1 has been developed based on our field trials this last spring, and we'll do another set of field trials and get to a V2 of the system. This can actually be used today, and we are doing tech transfer of that. Doesn't do everything, that's just a start, but it starts to put in the hands of the emergency response manager, in this case the wildfire manager, additional tools to manage airspace to get more benefit, more impact from those aviation services that are provided. Whether that's surveillance, whether it's comm, whether it's dropping water or retardants on wildfires, getting more from the use of the aviation assets. Next chart. So revolutionize engineering methods. Next chart. So, I said quite a bit already, on this. I think this is an area where I think NASA can provide a lot of unique value, but it is one where things are moving rapidly, and we want to partner with the community on this. Areas where we've got, I think, unique value is in, we have traditionally been a leader in the continuous and continued development of computational methods, computational physics, and so forth. But also in the testing of these systems to reveal the complex physics at play, the complex airflows and other things at play. And you can see in the images on the right-hand side, those are, sort of iconic, type finish images of those kinds of very complex flow fields. And by doing the experimentation where we've got, advanced instrumentation that allows us to really capture that physics, and then coupling it with our computational tools, we can really drive forward a future for this revolutionary engineering methods. And you can really think about it as it's not one versus or the other. It's if you go out to Ames and you see how the Ames Unitary, the 11-foot out there is can be with their high frequency pressure sensitive paint can be coupled in with CFD running on the high-end computing assets out there, and then visualized on their hyperwall. You can start to see how computation and experiment come together to, in near real time, be able to start to think about what's happening with the flow, why is it happening, if it's an issue, how can we do quick redesigns and get things back into test. But you can also start to think about how MLAI and synthetic models coming out of that could be a contributor as well. So lots of opportunity, excuse me, for advancement there. But it's not just aerosciences. It's maybe the easiest thing, the most, the thing that kind of comes to the forefront. But great work we're doing in materials and structures that is increasingly being amplified by the ability to develop these complex, these new materials like GRX-810 or shape memory alloys in new ways, using additive manufacture to develop lots of different samples and testing those. And then you get to a materials database that can be put together and made compatible with machine learning algorithms, then add AI and so forth, add computational materials methods and so forth. And so you can see how on the materials and structures side that you can also generate these kinds of advanced engineering tool sets that would allow us to move. So this is a really exciting opportunity where I think we need to kind of refocus on within NASA on the things we can do to really accelerate the opportunity in this space. All right, next chart. Aerosciences evaluation and tests are our big wind tunnels. If you go to the next chart, I think everybody understands, that we operate very unique facilities that cover the entire speed regime, everything from very low speed all the way out to hypersonic speeds, at scale, at test conditions that for at a wind tunnel are tend to be significant and unique, but these are large, expensive facilities. They take they're aging, so they take lots of maintenance and so forth. So and with reduced budgets, we're looking at ways to operate these facilities differently. So we've never, for these large facilities, campaigned across facilities. They've always had their own dedicated workforce and so forth. So each one is, again, reflecting the uniqueness of each facility. But can we think about how we might be able to campaign workforces across facilities, become more efficient? In the long run, that probably means we need to make investments in, control systems, data systems, and so forth, to really make campaigning a great way to do business in the future and get these tunnels as both efficient as possible and then available for testing whenever they're needed. So there's a lot of work to be done there as we move forward. I would just note that on the right-hand side there, that's the Flight Dynamics Research Facility, a new facility that will be replacing the 83-year-old vertical spin tunnel and the 12-foot stability and control tunnel out at Langley. And so it's really great to see a new facility come to life. It's going to be ribbon cutting on that is on November 13th, I believe. And then it'll start operations shortly thereafter. So it's great to see that even while that we have challenges with lots of older facilities, we can still see a new facility come online. So I think that's again it kind of is really indicative of how we need to have a long view of what the future is of our facilities. What is unique about those facilities? How can they contribute to revolutionary engineering methods? How are they utilized throughout the industry? How can we get higher productivity out of them? Where do we need, where can we just continue to maintain and upgrade those, and that will meet requirements? Where do we need to think about potentially new facilities where we know we're going to have a long need, 50, 60-year need for that kind of facility, that kind of data and so forth, that kind of testing. We're not going to be able to sustain some of these facilities, existing facilities, for that long. So a complex picture that our folks are diligently working through. And I think with that, that gives us a view of kind of where we are, where we're heading. Look, I'm not going to, not going to overlook the fact that we've got a lot of challenges as we head into FY26. We have had, folks, lots of folks leave with the DRP and so forth, and so there is challenge as we look to 26, but there's opportunity as well. And I think that's what we need to do is to keep a laser focus on recognizing those challenges as they come up and solve them, but also to keep our eye on what that future is. That's why we've got that, those transformations. That's what we're looking towards the future, and try to capture what those opportunities are to continue to deliver value for the aerospace community and the nation. So that's exactly what we plan on doing for the future. And with that, I look forward to your questions. So over to you, Rich.
All right. Thanks, Bob. We got a lot of questions that came in, and I'm going to try to synthesize several of them. A couple related to X-59. I'll start out that maybe pretty straightforward for you, but we're getting close to flying. Someone asks, what's the plan for announcing test communities where X-59 will fly? No,
it's a good, important question. There is a lot of work going on to assess, communities that would be that we could be doing overflights in the. Obviously, we want to get a range of weather conditions, geographies, building styles, population densities, all those kinds of things in order to get with the set of overflights. And right now we're, full success would be to do 5 campaigns of community overflights. And so we want that variety that will give us the best data possible. So we're doing that analysis. Obviously, we've got to have places we can base the airplane and fly safely and secure the aircraft and so forth. So that's part of it as well. So there's a lot of complexity in how we look at that. So that assessment's going on. We're not prepared to announce those. Those are that will be done very carefully. Obviously, the community itself will have a big stake in this. We don't want to announce anything too far in advance, because we want to make sure that we do this in a way that's that will retain good sort of scientific approach to to not having biased communities and that kind of thing. So there's a lot of thinking that goes into it, and so as we get closer to actual phase 3 operations, that's when you'll start to see, an announcement of maybe the first community.
Okay, there's kind of one other on X-59 that I think will let you speak to the relationship between this test and future industry versions, but it talks about X-59 as being a specialized design, carefully designed to produce a low boom. Do you think that'll set a standard too hard for OEMs to integrate into practical designs? So it kind of gets into test article, demonstrator.
Right. Well, part of the mission doesn't get as much airplay, because getting the standard is front and center. But through all of this, of course, NASA developed CFD tools and so forth that were, that it's been a really challenging process, but got to the point where we could actually do a full vehicle design for a low boom configuration and so forth. And all of those, as we get into, of course, we've done a lot of wind tunnel testing and so forth. But as we get to flight, we'll actually be validating all those tools. And so those tools are really the principles of low boom, and then the tools that allow you to to design vehicles using those principles is really what's required. And so, the X-59 is a specialized design in order to deliver an acoustic signature, and it's never meant to be a prototype or a instantiation of what a commercial design might look like. But those tools that we deliver will enable folks to then look at their requirements and what a feasible low boom design would look like.
All right. I guess one last one. I'm on the high speed area. There's a couple questions asking about civil hypersonics and how we perceive that. And I think you could say the relationship between civil and military.
Yeah, I think this is a classic case where, the military has a real mission need. They can take significant risk in pursuing that, but like many times in the past, the partnership between NASA and FAA there is extremely beneficial, because we're not only supporting the DoD in the pursuit of technologies that support their mission, but we're validating technologies that could find their way into potential commercial practice. And so whether those things could be, the first stage of a launch vehicle, they could be, hypersonic cruise, transport type aircraft and so forth. There's lots of ideas out there. Clearly the technical challenges are still very steep. So I don't think there's, that we're going to be seeing a commercial entry, over the next several years. But this partnership will, I think, push the hypersonic technologies and their validation for application in ways we haven't seen in many years.
All right. We're not without challenges, are we? There's a couple questions here about autonomy. So I didn't hear a whole lot about autonomy. One is about, what do you think the single biggest philosophical or ethical challenges to widespread adoption of level 5 autonomy, fully unmanned in commercial space? So maybe say a few more words on autonomy.
Yeah. No, that's a good question. I mean, and good point that I didn't talk a whole lot about autonomy, but it's certainly a key element of how we see the future. And I won't, I'm probably not the best person to talk about the philosophical challenges of level 5 autonomy, but I guess what I would say is that, there are two things that I think will drive, initial autonomy applications and so forth. One safety. Where can we, working in a human-centric system like we have with aviation, where can we apply autonomy to create higher levels of safety. So whether that's something that's collaborating or working on the flight deck with the pilots to create better situational awareness, to provide to provide options for mitigations and so forth, or whether it's something that's operating broadly across the airspace and so forth. I think that's one area, and then the other area is where you really need some level of autonomy to get to long-term commercial viability. So I think about advanced air mobility, where ultimately in a scaled advanced air mobility system where you're operating thousands or millions of operations on in any given day, well, you can't get there with having every vehicle have one or two pilots on board. I think there's got to be a path to remote operations, and then multi-vehicle remote operations, and greater levels of autonomy in order to make that happen. So I think but again, with safety as the underlying driver even there, right? So that's got to be where it's going to be as safer than having pilots on board, all those. So those are the drivers, and then I think it's a crawl, walk, run, right? And that's we've developed over the last, I don't know, a few years ago, we developed a V&V roadmap for autonomy, and I think that was an essential underlying component of that, right? Is that let's pull non-safety critical applications first, where we can do a lot of learning, and then we'll get into more and more safety critical as we go. So crawl, walk, run is as a development approach.
Okay, this is a completely different one, and I don't know if you're able to answer, but the question is about FACA advisory activities and understanding that several, including FAA REDAC, for example, have been stopped. Is NASA in a position to continue those? And the statement is, the concern from industry is aviation safety is dependent on these advisory activities, and suspension poses a climate of risk in this regard. So I don't know what you can say about that. But
yeah, I certainly cannot speak to FAA advisory committees.
But NASA,
I can speak to NASA. And there's a NASA, a NASA advisory council, NAC, that right now is not in operation. And so we have Aeronautics, we have a Aeronautics advisory committee that fits under the NAC, but right now it's not in operation. That's not it's not unusual, and when you have a new administration, for that to be put on pause, and there to be some reconstructing of advisory committees and so forth, and repopulation. And of course at NASA we have not had we don't have a permanent administrator, which is generally the key for for revitalizing those. We do, Secretary Duffy is acting, and he is very active. And we now have a permanent associate administrator. So I could see that being brought into consideration here, but I don't have any specific knowledge of a timeline for making that happen.
All right. There's another. I'm going to try to summarize this kind of long question, but it talks about a decadal shift between previously heavy government, private or government public R&D funding back in the day to more private sector dominance of funding now. And do you see that transition, and how does that relate to how NASA will relate with industry and academia going forward? So public, private, funding.
Well, we've always, I think for NASA Aeronautics, that's where we live, and in those partnership spaces where very often we enter agreements where we're bringing our experts, our facilities, our investments, and industry brings their experts and their investments and so forth together, and we do collaborative projects. So that's and we tend to invest more heavily in in lower TRL, and then we get more cost share as we get it to higher TRLs and they get closer to transition and commercial application and so forth. So that's just been our history. And so, with fewer resources for the time being, that, puts, we're going to have to be more selective and prioritize those, but I don't see us sort of changing the way we work.
Okay. There were two kind of related questions that I would put in the camp of, gee, our industry, it takes so long to go from concept to putting either ATC technology or vehicle technology into service. What are we doing to help kind of increase the speed of transition into service, which may give you a chance to say a little bit more about revolutionary engineering methods, maybe.
Yeah, I mean, certainly one of the thanks, Rich. And I think one of the goals, the objectives, metrics on revolutionary engineering metrics is the how quickly, at high quality, high fidelity can we get through our design cycles, right? So if we can speed up design cycles, be more efficient there, then we can get to market more quickly. And certainly the better we can more accurately and at fidelity we can simulate these really challenging physics. We've for quite some time we've been working towards CLmax, simulation, of CLmax, so that for certification flight test, you wouldn't have to do quite as many, certification flights to determine, and to qualify the airplane, certify the airplane for its CLmax conditions. So if we can do a better job simulating that and get high accuracy, which we have now done with the latest CFD techniques, now it's we need to sort of solidify that into sort of standards and then get credit through the FAA processes and so forth, which we've done in the past in other areas. So those are the kind of things that as we move forward, will help, right? This is always going to be, I think, a long life cycle industry. These are not easy systems to design, develop, and certify, but it can be helpful.
Yeah. We're just about out of time. Jim, do we have time for another?
Sure, let's do one more.
Yeah, there was a question about how NASA partners or works with international partners, and then along the same lines, the challenge of emerging China capabilities and specific note of high Reynolds number cryotunnels, so building of infrastructure over there. So speak to international.
Yeah. I mean, one of the motivations for the revolutionary engineering methods is, there is a lot of competition, and certainly China is a big player going forward. And as the question indicated, right? Brand new facilities, very capable facilities, and so forth. How do we stay? We've got a large fleet of existing facilities. How do we stay out in front? And I think we have to be thinking about not just, we need to match facility, but we have to think about what's next. How do we use, these facilities and computational methods in tandem using MLAI and so forth to extend. And, I think we really need to think differently about the future. To me, that's where, U.S. innovation, creativity, and so forth, can win the day. So let's not, get into they have this, so we need that, and really think about, okay, how do we think differently about how we do business?
Jim, I'd like to do one final one if I could for Bob. Just gives you, Bob, a chance to be visionary. So what does a successful U.S. aviation ecosystem look like to NASA in 2040 or 2050? So call it 2050. We're successful, the ecosystem.
Yeah. Well, I mean, I think, you would see certainly see on the sort of the airliner side, right? You'd see new generations of narrow body, wide body aircraft and so forth that are, that have ultra efficiency, that I think are at the beginning stages of really new propulsion systems that take advantage of new energy sources to drive ultra efficiency even harder. So new cycles, new ways of integrating cycles and so forth. So that's on that side. I think we'll see more, a maturing advanced air mobility system that includes both, small UAVs as well as eVTOLs and so forth, with a brand new transportation, levels of flexibility and benefit coming to cities, and smaller communities alike. I think you'll see, new regional, electric and autonomy is a great combination for revitalizing regional transportation. We're seeing some of that coming along today. Certainly, we're going to continue to see more launch, right? And so how all these things fit together, I think as we modernize the system and as we drive towards this prognostic system-wide safety, we're going to see improving safety even while we see advancements in all of these types of new vehicles and new transportation opportunities. And I think we're going to, on the maybe more subtly, but as we advance revolutionary engineering methods and as we continue to do this, we're going to see more and more. We see it today, right? We're seeing that entrepreneurship today because of, a small group of people can do some really high fidelity innovation. I think we're just going to continue to drive that even harder and faster. And so I think we'll see even more competitive landscape, even more folks coming in to innovate and really change the future in ways that maybe we can't anticipate today. Oh, and the last thing is, there's emergency response operations, I think, really crucial. They've got huge, wildfires are almost crisis level. I think, bringing aviation and maximizing aviation impact on emergency response management is going to make a real notable difference in our ability to get through these crises.
All right, thanks. It's fascinating. I think Aviation 25 was targeted at 2050, and in some respects 2050 is like a long way off, and in other ways it's right around the corner. We're just as close to 2050 as we are to the year 2000. And you think back to the year 2000. So no doubt we're going through a lot of change and adapting, and we're still going to be able to do a lot of really good work. I want to thank all the participants, all the attendees. I saw us get close to 500 online, and I did not get to all the questions, so I apologize for that. But hopefully I wove several of them together to give Bob a chance to answer them. I think with that, I think that's it. Jim, is there anything else we need to do to close this out, or thank Bob? And
so let me start by saying thank you for doing this for us today. We really did miss having you guys at Aviation 2025. Hopefully things will resolve themselves, and we'll have you guys back in full force at Aviation 2026. And I look forward to all the participants submitting their great work. You can find the link to submit your abstract or session proposal on the chart. And thanks again, Rich. You did a great job, and Bob, always a pleasure to have you on board. So thanks again.
Well, thank you, AIAA, and everybody.
Yep, thank you.
Thanks, Rich. All right.
Have a great week.
Starting tomorrow.
Yeah.
Let's have a great tomorrow.
Yeah.